All right, I'm very excited to announce our room speaker today.
It's not mine.
Oops, hello?
No, it's not mine.
Okay, not yours.
Let me turn it off.
Turn off your cell phones? No, so Louis Sentis is visiting us today from the University of Texas at Austin, where he is a professor in mechanical engineering and runs a lab called the Human-Centered Robotics Lab that he's going to talk to us about. And before that, he did his PhD at Stanford. Before that, he worked in the Silicon Valley at places like Fanuc. And he's going to tell us a little bit about the research that his lab is doing on things about humanoid robots and how we can do full body control of humanoid robots and safe physical interactions with humans and robots. So please. Well,
that's great, Andrea. Thank you very much. It is a great pleasure to give a talk at Georgia Tech. This is my first one here, by the way. And also thank you to Henrik, obviously, for inviting me. I don't know, is Henrik here, by the way? He's not here, right?
He's fundraising.
He's fundraising? Okay. Just wanted to say that about Henrik, that when I knew about him in grad school, he was a European icon. And when I learned he was coming to the US, I was, my God, his high energy can only mean awesome things to happen. And if you go into his CV and current activities right now, he's there from Universal Robotics to something called Robot Stocks, which is a fund from NASDAQ. And it's just such an activity that complements so well all the activities of the Robotics Institute here in Georgia Tech. So I'm definitely going to invest on those funds to do well. But I also want to grieve a little bit with you guys. I was a very good friend of the late Mike Stillman and feel very sorry for the great loss as a friend to the university, to Akiko, and to his family. Very, very, very sorry. So, just my words over there. So I'm very excited about many things about robotics, but one of them is the reports from the National Intelligence Council that come every 5 years or so. This is actually a report from 2010 trying to predict the technologies in 2025. This is called Global Trends. And at that time, talking to 2010, there were 6 key technologies that could potentially disrupt the world. And one of them is the extension of human life, which is biogerontotechnology. There were 3 on energy storage, and clean coal technologies, and biofuels, and so on and so forth. But the 5th one was service robotics. In particular, development and implementation of robots for elder care, application and development of human augmentation technologies mean that robots could be working alongside humans, but at the same time, a change in social responsibilities and employment might occur and might be adverse to low-income workers. And I think this is always the dilemma in robotics, and about any technology in general, of what is going to be the implications in the work environment. It's interesting that the Internet of Things was placed as number 6, which I would say that nowadays is more important than service robotics, but nonetheless still there. This is a report more recently predicting 2030 and robotics, service robotics in particular, of course manufacturing robotics as well, and UAVs and UGVs are here to stay and potentially may disrupt, if the FAA approves things, then may disrupt the world. But we need to focus on reducing cost, increasing intelligence, and also be subject to the scrutiny of the public. That's very important, being sensitive about all of these issues. And as a motivation, at least of what I do, let me bring this study from 2007. It's a European study from Spain, from a company called Fatronic, doing rehabilitation and bionic devices. And as you can see here, by age 70 and 80, by 80 in particular, we have 42% of the population that is fairly immobile, both for locomotion and also for manipulation. And therefore, given that our children, they're predicted to live perhaps even to 100 years, right? But we have these mobility problems after 70, 80, and 90. We really need to think about our lives and the lives of our children, what I'm calling after mobility. What's going to be our life after mobility? And I think that in this sense, robotics play a very important role. And my personal research interests are the study of machines and bionic systems with many degrees of freedom, not necessarily in a humanoid form, any form, to assist, augment, represent a human in any way that will increase comfort, productivity, security, and health. And this is really, well, sorry, and this is really a way to say that, that robots will be blue-collar workers. So given that robotics doesn't have really the metabolic requirements of humans, and perhaps we can utilize more energy and more resources, we might have more complex machines than humans, and they're really outperforming in a physical sense. And here we have such a machine. This is for the movie Robots. It was a movie from 2010 or something like that. With the robot, it has the anthropomorphic degrees of freedom, but it has degrees of freedom inside. It's doing another task, washing dishes. And I think that that's what we're going to see, of making more redundancy, more mechanical complexity, and of course more smarts for the tasks that we need. Feeling hopeful about those statements, if I knew I would succeed, and this is borrowing a sentence from Astro Teller from Google, I would have Home Assistive Asimos. That was views that I had in 2009. I would have Hume agile bipeds walking on alleys with children. That's a view I had in 2010. I would have rough terrain manipulation systems performing kind of the tasks that they perform in factories, but now outdoors and dealing with all this uncertainty of outdoors. I will have cloud-based humanoid laboratories where the students would download the applications with remote robotics, and they would take data, and everything would be safe, obviously. And then they would gather the data and then publish papers without really having to build those systems themselves. I will have physical human-robot interactions with many Valkyries for firefighting and for astronaut, physical human-robot interaction and human-robot interaction in general. And overall, I will have robots just moving around and colliding happily with people without injuring them. That's more recent vision. The main threat for all of those things is the human-centeredness of these things. The study of robotic systems for assistant augmentation, what I call an representation of humans to their comfort, productivity, security, and health, which is an elegant way to say that they should be blue-collar workers. So God knows what happened to Asimov's vision of crime detectives and civil rights advocates in robotics. So bring out the spirit, guys. From blue collar to advocates and detectives. That's a long haul. So within these kind of visions, the ONR Office of Naval Research was the second entity to fund my laboratory, but really the first substantial funding that I got back in 2011. Therefore, this grant is very significant for me. In particular, when I think about human-centered robots nowadays, my first reaction is to think about ONR and the Naval Research Laboratory and the great programs they have over there on predicting human movement, on the grammars for planning and so on and so forth, and as well on mechanics and the physical system. So if you are in these fields, these are phenomenal places to be at. And in there we play a role in the design as well on the controls of bipedal systems. And let me give you some history of agile mobility. In particular, my interest is on the speeds faster than 4 meters per second. Those have been achieved, but not as the regular kind of mode of operation that robots at all times should perform at these speeds. And therefore, I think it's a hard question to ask. And the motivation for those speeds is that humans, we tend to walk at 1 meter per second, 2 meters per second, but robots are there to in a way, to outperform our capabilities, and that's kind of doubling those speeds. So in my opinion, we should be aiming for those things, as well as being more metabolically more efficient and being lightweight and so on and so forth. But Locomotion has about 4 years history in starting in Yugoslavia, motivated by the injuries of World War II. And then it has really a peak in the 80s by Rayburn using what is called rule-based methods, which is really there's no proof of stability, but they just work by putting one foot in front of the other, just phenomenal. Linear inverted pendulum models, I think more rigorous, were developed championed by Honda and AIST in Japan, and arguably by Kato in the 1970s and Waseda Institute in Japan. Sampling-based methods championed by Latom and Tim Brettel and Chris over the years. Massive search, normally quasi-static but very skillful at climbing and doing awesome things. Robustness using the concept of capture point linear models by Jerry Pratt, where you now can push robots. It's also wonderful contributions on agility. A lot of focus on agility by Andy Rina as well, or Cornell. And now again, going into optimization and sampling-based methods by Emo over Washington, allowing robots to really do anything. Still, it falls a little bit short on real-timeness. Real-time is not there, and really real-time for locomotion is needed. You need the speeds of 2, 3, 4 milliseconds. He has some initial testing on what I call a toy-sized robot or child-sized robots. I have to bring up that it is not the same to do testing on child-sized robots than in adult-sized humanoids. In the same way that it's not the same to do something in an RC airplane compared to a combat airplane. The time constants, the mechanical time constants are fundamentally different, as well as the stresses on the system and the restrictions and the mechanical properties are very different. And I'm trying to make an argument that having a small robot doing something is not the same as having a Valkyrie humanoid that weighs 10 times more doing the same thing. But nonetheless, I think that this direction is the way to go. Specialized agility, cheetah robots moving really fast, 28 miles per second and so on and so forth, have been achieved again by Raybird recently, and in MIT by Sang-Bei. HMC also with concepts like the fast runner, very successful, nonetheless specialized applications. And point feet balance or walking has been greatly successful by Grisel, Jonathan, and Ames, who is now faculty in here. Just last week we had untethered locomotion, very, very hard to achieve. So great things happening on that agile field. Missing capabilities include the lack of a control and planning framework that is not specialized to one type of agility and can achieve what we call in control systems, non-periodic locomotion, and augmented with manipulation as well. We also lack hardware systems that can do it all. Can jump, use hands and feet for locomotion, and it's kind of a general purpose platform. And we lack real-time plug-and-play control middleware and solid APIs as well. We lack, especially when you do a simulation and you're porting it to your system, we lack automatic gain scheduling. We lack optimization of real-time parameters. We lack automatic calibration, diagnosis of sensor noise, automatic setting of filters, hardware checking, etc., etc. And all of those things is what makes these things incredibly hard from simulation to the system. In our research, we use the Hume hardware. It's a 6 degree of freedom, Sears elastic actuated robot, weighs 15 kilograms, fairly lightweight, can accomplish speeds up to 15 radians per second. We normally don't operate at these high speeds, and one of the reasons is because precision degrades, and point feet robots are already very sensitive to those things, to both the precision and the sensing post-estimation. We have a removable planarizer, so we are not confined to planar locomotion only. We have feed contact sensors for switching controllers and gains upon contact. We have a very low cost, bad decision in my opinion, microstrain IMU. We should have gone for the high performance one, but we augment the system with a phase-space motion capture system at 500 hertz. Obviously you have suffered some occlusions and other things, so we have to do sensor fusion there. We are based on Linux with a real-time kernel, and then we have simulations. And the simulations is funny because a few years ago I thought I would never use simulations, and how important they are, obviously. We rely on prismatic inverted and pendulum dynamics in order to allow rough terrain locomotion. This means that we are not confined to a plane. We now can go in all directions in the vertical axis. And if you assume that your robot is a point center of mass and a point foot connected with a prismatic body, you can derive the second order dynamics. It's a multivariate nonlinear differential equation here below. Now, if you assume that you know the plane of locomotion moving up and down, then that can be simplified into a nonlinear ODE, and now it can be numerically solved, okay? So given apex conditions, initial conditions, and known foot positions, now you can do forward and backward propagation and predict your progressive movement or your cyclic movement as you wish. We exploited that at the beginning for our first attempts at dynamic locomotion into a concept we call phase-space planner. The idea is to find the switching states between neighboring contacts. So let's take here curve 1 and curve 2, given known apex conditions, so the bounding conditions. The question is how to switch from dynamics of curve 1 to curve 2. And the phase space, which you see here, the space of position and velocities in the center of mass domain, naturally yields this answer as the intersection between curves. Thus, locomotion emerges by switching at those points, and this particular point. So a very simple, intuitive strategy that works for just any type of locomotion. So that planner was derived already a few years ago, and really we started to publish it, but it had a relatively minor impact. And the reason is because we didn't have a system that we could implement it on. So my last years have been really trying to push the testing of those systems. Also, when we started testing these schemes, we found out that fixing the foot positions meant that the speeds, the swinging speeds were variable, and the swinging speeds means that we have different precisions. And because our controllers are very sensitive to precision, we decided to switch to a cousin controller, which we call the constant time to velocity reversal online replanning strategy. Also, our strategy here is by replanning at every step, so we can adjust for the uncertainty. In here, foot positions instead are searched at every step, such that zero velocity will be reached within a given set time. So we start with a known state on the left or the right-hand side at the bottom, and a known foot position. And we started lifting the foot. We plan the next switching state such that there will be a constant time to velocity reversal. We'll reverse velocity, so we'll be coming back and forth at a constant time. And therefore, our swinging trajectories are always at the same speed. That was proposed by my student, and it proved to be hugely successful, at least in simulation at the beginning. So we have here, we implemented this is a Korean package called SRLib. It's a physics-based simulation. We also implemented whole body operational space control, which is a general purpose controller. And as you can see, we enter a limit cycle with minimal drift. We have here 3D locomotion, this is untethered, and very good results about a year old. And obviously the question now is how do we put these capabilities into a real system? We also started to study robustness. In here we poke it, actually we simulate errors in the landing. So we are on this regime and we have planned this constant time to velocity reversal trajectory, but we force an error on the landing position, and that causes a progressive step. So when we lift the next foot, we are already planning the foot placement, the switching state, so that we will have again constant time to velocity reversal, and that allows us to enter again a periodic cycle. Again, I mean, our focus actually is not on periodic cycles, but this emerges naturally. And the Y direction, the lateral direction, is planned in the same way, and it's robust in the same way. So it proved to be quite robust strategy. So I had the placement planning strategy, or we had an online robust replanning strategy. We were experts on whole body control. We had a robot, so I thought it's going to be a piece of cake. Within 6 months we're going to have it. But it proved to be wrong, and the reason is because there's all this other list of technologies that we needed to develop in-house. We underestimated the need for body pose estimation, impedance control of the series elastic actuators, which is very hard when you have latencies from whole body control, floating-based inverse dynamics, which I had used extensively in simulation. It proved to be very difficult to implement it into point-fit robots. And then switching contacts, the transition between the sharp torques, it was also a different strategy. Let me here point to high impedance control of SIAs. This is the Hume SIA developed mostly by Mecca, but also with one of my students who ended up being an expert in SIAs and making a thesis on SIA actuators. This is a typical control loop. It's a nested control loop with a torque servo, and then it has here a position and velocity servo. And this suffers from two problems. We imagine that the position servo is actually operational space control. It suffers from latencies from communication buses and latencies from the computation themselves. It turns out that the velocity servo the only velocity servo is extremely sensitive to latencies. So any thing beyond 1-2 milliseconds is gonna produce instability. So you have to be very wary of these things. The second thing is that the torque servo allows the actuator to perform as an ideal torque source, and therefore there is no natural passivity, there is no friction whatsoever. So what you have for your advantage for damping your position servos is now gone, and everything has to be relying on the velocity servos. But we said that the velocity servos are pretty bad. So dealing with high impedance on SIAs is very is very bad. On the other hand, they're great feed-forward controllers. If you have very good pose estimation, then you can now relax much more your feedback controls and rely much more on feed-forward. But for that, you need to have very good pose estimation. So we have spent the last 6 months becoming good at pose estimation. I have a student that uses the phase space feedback. It's very easy to compute absolute orientation and position using phase space system by minimizing the square error between the observed motion capture system and the known marker locations. You need to augment that with Kalman filters, including the IMU data. Some of the challenges we're dealing currently is flickering markers or partial occlusions, the complexity of the model for Kalman filters, but I think that within a week we're going to have very good velocity estimation. Now, if I would restart this project, I would probably choose the KVH1750 IMU. It's a 17,000 IMU used in tactical operations, but also used by people like Jonathan Hurst and Griesel. When you have these IMUs, you really don't have to do any major sensor fusion. You have it readily from the system because it's extremely precise based on fiber optic gyros, very low noise accelerometers, and so on and so forth. So we are dealing with this additional hurdle. But on the other hand, I think we're going to have perhaps a publication in estimation, which is a great thing for us. Now, our real objective, or my personal real objective, is not so much locomotion, but is whole body capabilities. In this sense, I utilize something that I developed during my thesis, floating base inverse dynamics written here, where we have floating degrees of freedom. We have also the contact forces, and then we can now pose the problem as with the natural constraints imposed by the context. Something I developed for my thesis is this contact consistent Jacobians. They're consistent with conservation of momenta and also with the contacts, but at the end you're mapping actuated joint velocities to operational space objectives using these modified Jacobians, and this allows you to use plain vanilla operational space control, which is a well-known strategy, model-based, and you can do unified. What is important about operational space control is that you can do unified forces and motions, and both of them are interesting for locomotion. Now, many people will ask, why do you need forces for locomotion? So I will present the case pretty soon. I work also during my postdoc on the force problem, and then recognizing that humanoids, they need to move, but also they need to control the interaction in the environment, and that was posed as a problem of finding the orthogonal space to accelerations. That torque space belongs to the internal forces, and it tells you how is your grasp, but also what is your capabilities for acceleration and moving around. It's not the same to start cold and start running than having an additional contact and then produce a different type of mobility. So that's research on hold right now a little bit, basically because I have a little bit of opposition from my students. I don't know, maybe they find it hard or what. But it's a great area to investigate, multi-contact agile locomotion. So in there, another advantage is that you can do feedback control of the internal forces. You can compute this set of internal forces, and because it's fully controllable set, you can now do sensor readings of internal forces, and now you can achieve very accurate control with your environment. So we took those ideas and then we produced a controller, we call it whole body operational space controller for our bipedal systems. In here you might recognize operational space control, the weighted feed-forward matrices with gravity compensation, thanks to the pose estimation, the Jacobian transpose projections. Here we have a focus not only on the desired trajectories, but also in gain scheduling. Depending on your interaction with the environment, your gains have to be fundamentally different in order to adjust for the changes on impedances. This is something very typical of these robots that change weight very, very quickly. So that's an augmentation of our control system with gain scheduling. And here is the big novelty is the feedback, the desired internal forces, how precise you want to be with the environment. And then in here taking the torque sensor readings and then projecting them as a sensor internal forces and doing feedback and then achieving precisely your behavior with environment. Why do we need internal forces? Well, for all the types of locomotion, that planar locomotion, we are interested in this type of locomotion in any medium with any degrees of freedom. This is a robot that, if it gets funded, is going to be built. It's called Triskelion, and it is moving on these spaces very quickly. and therefore it has to reason about these internal forces as well as the manifold of possible accelerations. So we have to control them very precisely. So these blue things are internal forces. And here, obviously, if you're doing this kind of spider type of walk, like you do in the Ninja Warrior, American Ninja Warrior thing, right? This is what we're thinking we have to go, just for the sake of exploring every capability, because it was a great trait for adaptation from early humans, and because perhaps future rehabilitation systems, they will require people to go to the mountains and run with the kids and go to the trees, which is now not possible, and there those things play an important role. So when we put these internal force controls together, this with zero internal force control, right away it falls because it's not, the gravity is pushing it down, it's not compensated. But as soon as we increase it to 100 newtons, internal forces with feedback, now we can start performing complex trajectories on these environments, and we can be extremely robust through feedback to very, very hard disturbances, and given the harshness of the environment. So this, is just a proof of concept, but we want to bring it farther. We want to be doing a spider walk, jumping, and so on and so forth. Now, our second interest is in locomotion. So these results of about 2 months ago on the constant time to velocity reversal planarized, and here responding to disturbances. What disturbances? Control precision, which we still are tuning a little bit, and also our post-estimation velocity is still not good enough. So it has this. But you can see it's a non-periodic thing. You can also see that the hanger, it went off to the point, and he didn't notice. So I'm not showing the end of the video, right? Because the robot just falls over. So really, this is locomotion without tether. Now these are results of last week. This is trying to get to untethered locomotion. As you know, Atrius already fulfilled that capability last week. And we're trying to get there as well. Not so much competing with them because we're going into the whole body multi-contact thing. And these results fresh from Valkyrie by yesterday, where we are able to do already 3 steps, completely unsupported, still not quite there, and very quick. I agree. But I think that within 2 weeks we're going to be doing untethered locomotion, and that's very remarkable for me because I am a manipulation person. And I came to this field just a few years ago, and now I'm able to compete. I hope I can compete with the best of the best out there in a few years. Let's switch gear. We received an NRI in 2012, so thank you, Henrik. I mean, not that he played a role there, but thank you, NASA, and so on and so forth, for bringing this program here to the US. What we propose is a precision outdoor industrial level mobile manipulator that could actually perform very accurate tasks in the sub-millimeter region, but now with all these disturbances. And it came back funded by NASA, and that was very interesting. And we received a call, and they said, we're really interested in these technologies because it's the same, it aligns with our plans of sending astronauts to Mars, building habitats, building instrumentation, and so on and so forth. So all money is welcome. And then we went on. This means also changing mentality because we were in the willow garage sort of mentality, and suddenly we had to change. But now we have embraced it, and we're really happy working for NASA. Precision mobile robots is inferior to industrial manipulators, in part because the rigidity of this system. If you take a KUKA system, very rigid, and all of it is for minimizing flexibility of the system and achieving the accuracy. In part is because the odometry. So certainly those are important things. Accidental collisions will happen to these free roaming systems, so that has been a focus of ours. And then autonomy needs to happen, obviously. And then proper APIs and proper software, it needs to be out there for achieving these capabilities. This led to research of us in 2012-13, published in RSS and Autonomous Robots, into rough terrain mobile manipulation. And for that, the rough terrain, the robot has to balance, so we started to implement whole body, these general purpose controllers, whole body control, in Dreamer, and creating an API that could be used. The API was open source with help of Willow Garage, focusing on the real-time performance, not quick, but very quick, and therefore we could have stability, redundancy as well, kinesthetic interaction. And this is, you know, a proof of concept at the time that produced a couple of good publications out there. And then going into much rougher terrains and kind of imagining what happened if these guys would be out there, humans would be around. Not shown here is that the robot at a certain point just jumped off the board and then it broke in 5 pieces. Right? So my son says, never show robots breaking, they will fire you. And I was like, no, I have to show it, right? So it's like, no. So anyway, it also led to safety studies. This is a little bit of ideas that we run in 2011. There's a lot of studies in safety, by the way, but almost all of them focus on the upper body. So we decided to hit the lower body. We built educational systems, mobile bases. This undergrad project has been running for a while, funded by NASA. One thing that I said is that every student can handle a maximum of 3 degrees of freedom. Maybe I'm not ambitious enough, but this base has, instead of caster wheel, has these ball wheels, can handle obstacles up to 2 inches, has a suspension system, but most importantly, it has a reaction torque sensor over here that measures the reaction torques on the wheels. And we hope that by triangulation, we can measure the forces in any place on the body. So we should, for being the first base that has whole body sensing, including the wheels, right? And this is without a skin. If you want to accomplish these capabilities, you need to have a very good idea of what people are touching. And also you have to have a very good idea of what is an uncertainty or what is a certainty. What is a certainty is all the mechanical parameters. We augment our models with roller degrees of freedom. The roller degrees of freedom is not the wheel, it's the side rollers. And we estimate the friction, we measure it, and we fit a model. And with that now, we can remove everything that is known and concentrate on triangulating and obtaining the external forces to contact. With that, assuming a planar model of contact, we can now detect location, magnitude, and direction of the forces with a 20% error from any place, the wheels, the body, inside of the robot. We build an experimental facility where we can repeat the same forces or the same impulses when we hit the robot, and we had this educational base built by undergrads. Actually, this is the previous version, my apologies, over here. And then we conducted this sort of academic study where the focus were on the reaction time. We believe that safety has to do with the reaction time. We have about 100 milliseconds of reaction. That's not good enough. In part is because of the estimation process. In part is because the gear trains, the harmonic drives, are relatively slow. They have time constants of 20, 30 milliseconds. The structure itself is not rigid enough. So we want to start shooting for, 2, 3 milliseconds reaction times. If your robot, you touch it and you just reacts with very low impedance, it must be a safe robot, right? Unless it hits somebody else on the other side, right? So we went into this study, which ultimately it allowed robots to move around people, and to prove that it can sense contact on the hands, on the wheels. 50% of the collisions happen on the wheels, right? So here I put my hand, which is a delicate part, and is detecting the direction of the collision, magnitude, and orientation. And here, just a wire, right? So it's that sensitive, right? And here kind of envisioning, he gets hurt, right? But still, it's pretty low impedance, right? And people are happily reading in the park, and robots are colliding. Oh, how cute, right? So, yeah, always is happy to volunteer for those things. And here a little bit this proof of concept, we can touch it anywhere. This doesn't have a skin, so we advocate for not having a skin. Why? Because you're gonna have a skin on the wheel, and the wheel is responsible for 50% of the contacts, so we wanna have 100% safety.
Oh, okay.
And so on and so forth. Okay? Now, meanwhile, we were involved in the DARPA Robotics Challenge as every other team in the nation. We team up with NASA on building actuators and controllers, both controllers at the low level and also controllers at the high level. And we started thinking about the design, and we thought, and then the robot thought with us. And that's where we got there. We became very thoughtful. We had a very hard time on the DRC, as you guys know. We were incredibly ambitious. It's a full body, cirrus elastic robot with a lot. It's over-designed, but on the other hand, we went along with the vision of NASA, which was kind of a biped instead of having something that was a quadruped, and with a lot more payload capabilities, more range of motion, and we paid the price. But if you have seen latest movies of Valkyrie, it's now in great shape. Actually, in a way, it's performing similar to Atlas, walking, balancing on one foot, and so on and so forth. But we didn't do well on the DRC, I must admit. We locked ourselves in the Apollo Lander room in Houston for 15 months. Actually, I had a pseudo leave of absence there. I was working until 5 a.m. myself every single day. Sometimes I would sleep in the car. It was harder than my PhD. But I knew that it was a historical thing for us. We developed mechanics. This work by my student Nick Payne, very talented. This was published in TMEC in 2014 and has subsequent publications. This was an enhancement. We thought that CS was all done, but he was poised to make it even better, in particular to achieve the performance of hydraulic actuators, that power density. So he focused on, rather than using the MIT style CS, he reversed it, and rather than driving the ball screw, driving the ball nut, now the ball screw goes inside the actuator, and therefore there is a piston-like drive on the back. And also the spring is on the rear. And that allows us to make an incredibly compact, incredibly lightweight performing hydraulic actuators. So these are 450 watts per kilogram. Again, hydraulic performance, extremely fast, precise. As my student says, it can lift a bear, and it can sense a butterfly landing on the bear. Okay? So if you are not into mechanics, it must be hard for you to understand that, but this is really high, very high performance, right? Moving on, well, as I play back, and if you pay attention, the spring here, the reverberations of the spring, and doing the measurements and the model-based controllers to achieve the desired precisions. This is very, very nice work of his. Now, when he started developing this research, it was accepted outside without us publicizing it right away. We have suddenly China producing an industrial version. Is about now to become commercial. We don't know if it's going to have a market or not, but seriously elastic for the industry. NASA came in and developed the Valkyrie ankles, 4 of them, and then the 2 degrees of freedom of the chest, based on CS, even on UTCS. They entertain even making the entire robot using UTCS, so we play a very important role there. IHMC built their rehabilitation devices based on plain vanilla UTCS, where this research being published. NASA and HMC, they embedded those CS in the X2 Mina exoskeleton, now also under publication for paraplegic individuals. And those came without really us publicizing. We're really happy. By the way, the university didn't allow us to patent this thing, so it's open source nowadays. Well, we're moving on now. We're moving to liquid cooled systems, low-cost liquid cool, moving at $500 per actuator. We believe that future manufacturing systems, they was talking to Henrik, they will be $2,000, $3,000. And they will be extremely lightweight, extremely precise, and that can only, in my opinion, be achieved with liquid cooling technology. So we're building those things under Chinese funding, gearing also to commercializing. So our involvement with Valkyrie over here, that's a video that my student put up. We spent there 15 months doing a lot of work on the rotary C actuators, the linear C actuators that were motivated by our actuators on the body, doing a lot of low control at the beginning. Here is the UT-SIA transformed now into a NASA SIA. The same concept, doing a lot of testing, very good force control, obviously. And on we went there, sleepless, doing force control, testing, more testing, and then ultimately we went to the competition, and we performed poorly. But we had phenomenal whole body operational space control on the upper body. Unfortunately, the legs were not working at the time, so we didn't have the ability of walking. Manipulation-wise, we were, in my opinion, one of the top teams. Here, whole body operational control developed by NASA and us. And as you can see, Hume is controlling the robot. So this is the API, the whole body control API, Cartesian, dealing with redundancy, connected to something called RTC, Robot Task Commander, which is an engine that allows you to connect controllers, control primitives, let's say the control primitives, with the planners. And then also augmented by affordances. And those affordances can be fit to the environment. And with one hand, single-handed, she can perform this type of tasks. And now this, in the last year and a half, we have been cleaning up this software. It is now finished, but has been submitted for publication. Very originally, it's called Controllt instead of Move It. I opposed to the name, but my student absolutely wanted to call it Controllt. It's a middleware for whole-body operational space control. It supports Ubuntu 12.04, 14.04, ROS Hydro, and Indigo. It supports Eigen 3 instead of Eigen 2. It has RBDL for rigid body dynamics. It has URDF robot descriptions. It has robust bindings and services. Plug-in architecture for the user to design their drivers and connect them to the different robots. Also to the real-time clocks. There is plugins for the real-time clocks. Has YAML configurations for specifying the behaviors and also focusing on this gain scheduling and a little bit of more introspection into those things. It has Gazebo 4.0. So what are we waiting for? We're waiting for the release from NASA, which is a very important, difficult process. We're shooting for an LGPL V2 license, which is the only thing that UT accepts, not V3. And then hopefully, you know, I wanted to have it ready right away, but it's going to take some time. I don't know what the adoption is going to be, but we're excited about it. Futures, we have a strict whole-body operational space control API, basically on compound tasks, which are the motion primitives, constraint sets, which defines the natural constraints of the environment, and also the actuation constraints, drivetrain constraints. We have whole-body controllers as well. We're trying to move into supporting both WBOSC controllers and also IK controllers. It has a plug-in architecture. It has a multi-thread architecture as well, the servo thread model updater and task updater, and it runs incredibly fast. It runs 10 times faster than our architecture 2 years ago. It can achieve 2 kilohertz and really 2 true kilohertz with 30 degrees of freedom. So that's going to be good news for precision control and so on and so forth. And this is a video we submitted recently for publication of that middleware that we have here, a product assembly task. We are very oriented towards collaboration with this company on manufacturing. There is no visual servoing here, unfortunately. So this is just utilizing the resources, the API, and proving that it's very easily. We're connecting to a Smash in a ROS as well. Visual servoing is coming as well right away. That's not where we come from, but we are being hard-pressed to perform at this level as well. Here we have the operation with redundancy. Redundancy is used for optimizing the reachability workspace, and that has to come naturally. So we want to have kind of a universal cost function that does it all. Potentially we could learn them as well. I think that maybe with Andrea, using stuff from Andrea would be a great thing, and so on and so forth. And I think I'm done. So thank you.
Time for questions.
Yes, go ahead.
So will humanoids beat humans to Mars? Or
sorry, if...
Will humanoids go first to Mars, or will humans free?
So NASA just now issued a new BAA for what they call the Space Robotic Challenge, SRC. Very original name, you know, just change the D to the S. But I think it focuses on that. Depending on who you ask, NASA themselves, I don't think they have a single line of thought. Actually, Valkyrie, when we didn't do well on DRC, I thought it would be killed, the project. And it was bad for everybody. The money was invested. But suddenly, the management at NASA became in love with this project, and now it has very healthy funding. Not to say that the Navy has very healthy interest on those projects and might be funding this research as well. So, depending on who you ask, I think NASA would be very interested in having, you know, what NASA vision is to have habitats, and you cannot have, humans are much more costly, so if there's going to be a justification in costs, we're going to have humanoids first, or together at the same time, but with less human personnel. Does this answer your question? But I'm not a NASA spokesman, so, you know, I just kind of feel. Yes?
Could you comment on the home health care application?
Well, yes. So, I mean, I don't have a complete focus on that. I think, you know, but I have had thoughts about going into this direction. I think that it's a hard problem because navigation on the space is difficult, and I think maybe overhead robots, they don't have to deal with the motion planning. They just retract, fold, and then, you know, the idea of the iPad, you're in bed and you have your API, or, you know, and you you drive your robot overhead and that doesn't collide with things, open the refrigerator. So I think there's possibilities. Now, everything is the market that is out there. We have healthy funding from a Chinese manufacturer. I try to drive them for health applications. I said, do you want to invest in us making this application? And they said, no, we just want to manufacturing. We have a very clear idea of the size of the market, and let's not go there. So I cannot comment too much, but I show some pictures of rehabilitation and exoskeletons. I definitely think that life after mobility is a huge market because we're going to live until 100. That's what I want, right? Yes.
Quick comment. Because of China's one-child policy, it's going to be a huge market for elderly care in the near future. But the question I wanted to ask was, what are your opinions on energy-efficient walking? Also, sort of curious to hear that because you can't run these robots on the battery packs right now.
Right.
15, 30 minutes.
Right. Well, I think that should be a major focus, both for locomotion and also for manipulation. And we're trying to convince our partners in China to focus on efficiency even for manipulators, right? Overall, if you're going to have in the assembly lines, they have hundreds of manipulators. So if you are 50% more efficient, you're going to save quite a bit of money. I think autonomous systems is the same thing. Now the question is who's going to use biped systems, and I think there's very divided opinions. In one hand, talking again to China, mentioning out China, right? But I'm motivated by that, right? They like the idea of the kind of the clone, the humanoid clone, right? So you have a robot that represents you or is a doll, and then I think there's a market for that. I think in the US really is more of a firefighting, ONR type of research. DARPA things is very defense-oriented, and there again, right? If you're gonna do a mission with peacekeepers in a city, and we see now the Squad X core program, right? They are considering as well using humanoids, but they have to enter the town. They have to be there for half an hour. The robots have to be going up and down stairs. I mean, you need quite a bit of efficiency. It should be a focus of us, absolutely. All right. Yeah, so, go ahead.
Yeah, you mentioned that for the DRC you focused on biped based on NASA, what they wanted. What would be your choice if you could choose? Like how many manipulators? How many? Would you go with quadruped or have something more like 3 legs, like some of your other concept sketches?
I think that we were involved there from the beginning, and there was this conversation. So we. I had a little bit of an influence capability, but not 100%. I guess that I like the CMU concept quite a bit, and I think that if NASA was there to win, they could have gone, and they probably knew it. They could go on the CMU way, but Houston decided not to go there, and I think that they decided for a good reason. Houston is the human operations center of NASA. So they have to really justify the cooperative. So they, in my opinion, they used the DRC for developing a helper for the astronaut, and that had to be that system. So they took the right decision, but they didn't take a decision for winning the DRC or even competing well. So I think that the only thing that the mistake here is to have high expectations. I think if you ask Aaron and myself, it was clear to both of us that was a longer-term project. That was not there for winning right away, and we would not have the capabilities. But we're really excited because we knew that this robot had a life after that, and sure enough, now it's well funded and it has a life after that. So mixed opinions. I'm happy there's a humanoid. I'm happy that there's support for humans. If we were here to win, I would have chosen something more along the lines of CMU or JPL.
Great. Let's thank you.
All right. Thank you very much.